Thank you. Thierry, we have to change our titles because you have to add theory. I have to change and use yours and say experiments because it's exactly the continuation of.
You notice that I didn't show experimental curve. I knew what was coming next.
Are there other experiments? Okay. So this is actually an experimental talk, exactly in the idea to try to find exactly what the prediction that Thierry showed us in a minute. So has been done with some people of my institute, some other from Paris, and Alberto and Laura. Let me start with a movie because you didn't put a movie, so I put it. And but this is a, let's say, I call it this a commercial movie in the sense that it wants people, especially magnetic community, that like to see something because this is not exactly the kind of bubble expansion. So the creep experiments that I'm going to show you, which is much more boring than this. This is fancy, so I like to start with this because this sample is 1 nanometer thick and it has been irradiated. So there are pinning points here and there. So you see that sometimes the wall gets stuck somewhere and stays forever. Some other times it depends. So the pinning is a real stuff in some sense in magnetic system. At the end, it does this kind of Mickey Mouse ears, as I like to. And of course, this is much more difficult to study. Okay, a bubble which is smooth and circular is fine. Here, there are problems. So this is more for the future, but we develop a code to be able to analyze and find the contour and many other stuff during the motion. And so it's very clear what is the pinning here. Here the color is the time, so it starts from black up to white, and this is the motion of the wall at each time, okay? So this is more or less my talk. I will skip the introduction because, as you say, I will say theory here. I will go to experiments and I'll discuss the results. In some sense, nothing is new. I use exactly the same terminology and the same consideration of theory. Just a motivation from the magnetic point of view, there is an explosion of discussions and papers to use domain wall as spintronic device. I don't go into the details, but the idea is we can use the domain wall to make memories like in three-dimensional way. Sometimes I don't believe it to anymore, but never know if it's real. There are new ideas, but anyway, the point is to try to understand what happens exactly when you apply small fields or small currents, so in the creep regime, because temperature here, of course, is extremely important and can change the situation. So I don't discuss this because you know very well now, and even that is the same picture of this very important old paper. But I want to point out that with this picture, the 1/4 description, there was another important estimation of the roughness exponent, which, of course, the data are compatible with a large number of estimations. Sorry. I am an experimentalist, so sometimes I feel the duty to say that the error is pretty important. Anyway, 2/3 is aligned more or less here, so it's compatible with this, but it's fine, yeah? Okay, it's fine. But anyway, this was the idea that this 2/3, as Thierry told us, is coming from the equilibrium, okay? Well, I skip because the idea of universality was much more let's say, general than expected because Jeudi and others collected many different samples and found that also the distributions of the energy is very universal. So they add this -1 and magically all the samples, all the material fits perfectly the prediction, which is really amazing. And then the focus of my talk is the realization, the experimental realization of this idea that Thierry explained us. So can I see in my system the cluster, so the idea that I have events that are correlated in space and time and well separated, okay? Here, as Thierry has shown us, the real important parameter or length is the optimal length. So this characteristic is length, and so I have the problem, what is an experiment, this guy? Because everything depends on this. If I am able to estimate and understand if I in this regime or in this regime, it's extremely important. Okay? And then this already been discussed, and I will focus on both curves in a minute. So, what we use this sample, which is quite typical in spintronic studies. This is a cobalt iron boron of 1 nanometer. You know how large is 1 nanometer? You know? In this case, plus minus 2 or 0.2 or something. Because, believe me, I can see one nanometer of material. It's 2 or 3 atoms or something. But what is extremely incredible is that this guy is 1 nanometer, but he stands perpendicular to the sample. And so, can you imagine the spin all up? Which is, I mean, strange because the dipolar interaction wants to be up and down, up and down, up and down. You know, if you play with the magnets, they don't want to stay north, north, south, south. They want to say north, south, and so on. Maxwell equation, okay? But they stay perpendicular. The movie I show you is a bubble where the inner magnetization is up and outside is down, which is amazing in 1 nanometer sample. But because MgO has a very strong orbitals, the magnetization prefer to stay perpendicular, they stay in plane. If you go to 2 nanometers, it goes down in plane. So these are very particular but extremely nice material, which are considered to be the material of the future. Okay. It creates the magnetic anisotropy. So it wants to stay, the magnetization wants to, the spin wants to follow the magnetic anisotropy, and the MgO creates the anisotropy. Exactly as platinum on cobalt, which is the experimental ML and other experiments. So the two big families are cobalt with platinum and cobalt iron boron with MgO. So they have to match also the lattice, the distances to have these properties. What's next? Okay, my experiment is, it's an experiment, so I have to take images of the motion of the bubble, okay? The best I can do is take 5 frames per second. I want to do a fast measurement in the sense that I want to know time, and I mean, with the highest resolution I can, what is the motion of the wall. But here there is the other important point. My resolution in space is of the order of 0.3 microns. There is no way to make it better. You can go down in 0.1, but more or less this is the resolution of the best CCD camera you can have. Okay. The other thing is that I need to stay in the creep regime at the smallest field I can. Okay. So more or less I'm of the order of 1% of the depending field. Okay. I can do, well, in principle you can do, in Bariloche they do experiments at much lower field in some sense. But anyway, at these low fields, I have to do, let's say, a set of experiments because recording everything is impossible for the memory of the card. So I do steps, I do sets. In this case, there are 8. So this is an image when you see that the bubble is growing. I stop the field, I acquire the data, and I go on every time. Okay? How do I make the image actually? I try several procedures, standard procedure to get the contour of this bubble, and it's a mess. The only way I found is effective is to try to understand, for instance, consider this pixel A, the red one. This is in this situation is at a certain gray level, which is, for instance, this. When the bubble, which is another gray level, pass this point, it changes color. Okay, so if I'm able to understand where these sharp changes occur, I can say, okay, the wall passes. Sometimes it's not so easy for the pixel B, the blue pixel. Sometimes it's more difficult to understand where is exactly the time, exactly the frame when my pixel changed color. Okay, and so we have to consider that this is an experimental problem, and because we want to compare with the theory, we need to understand how this can affect the final results. This is typical when we try to compare theory with experiments, because sometimes you think in the experiments that is exactly what the theory describes, but is not. So for this, the first thing is to understand what is the optimal length in my experiment. Okay, doing some calculation, blah, 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 it doesn't matter so much, but this is the order of magnitude, 300, 400 nanometers, so 0.3. So this guy is of the order of my pixel size. I can't, so the consequence is that I cannot see the events which are much smaller or smaller of the order of this characteristic length. I'm above. I'm see the dynamics only above it. Okay? If you remember this change in the slope of the size distribution, I can only be in the upper part. There is no way. We spent months to realize that we were looking just at where we supposed to have clustering of the events. Okay? And there is another problem. When I say, okay, in this pixel the frame is number 10, and the size of my pixel is of the order of optimal length, this is not an event. It's already, it can be a small cluster of events. So, because I cannot detect the events itself, okay? But I see that just looking at the different colors, there are regions which are switching at the same time. So these are parts of the world that switch together, okay? These two colors are close to each other. So maybe it's just an experimental error that, for instance, this guy switches at 100, these guys are 101. Because the experimental problem to detect exactly when this happens. So if I just simply check if these pixels are in a row, are consecutive, I can find this black region, which I color with the same color, that gives you the idea that you have a correlation, okay? It can be an experimental problem, but it's not. There is some physics there. But we need a more robust way of estimation the correlation, okay? So we took the idea from this paper of Bayesi and Pakulski of a few years, 10 years ago, which is very technical, but the idea is the following. If you have a random Poisson distribution of events, it's very unlikely that you have events that are very close in time and very close in space, okay? If you consider how many of them that have this quantity, very little, if they are randomly distributed, this number is small, okay? But if you do measure this number large, it means that if two events have this number quite small, it's possible that these two events are very, very correlated. Because if you find two events that have this number very low, which is very unlikely, it means that they have to be correlated. Okay, this was the idea of Bayesi. How can we translate in our bubble expansion? We thought that it's roughly the same. So imagine that I have an event here and another event here. How many events I can have here? Well, this is something like the area of this guy, okay, times some probability. So if I consider a second event J, I want that also compute the probability that my size can be larger than my father, which is Si, okay? If you calculate this, you find that this number can give you a measure of the correlation, okay? Because it takes into account the probability in some way to find events in this region, okay? How can we translate this in the experiment? Oh, it's quite simple. We calculate this guy, so we calculate the angle, the time delay between these two guys, and the average time between them. And we make a distribution. The real data, so the color pixel that I was showing you before, are compared to all the others, and we select the ones who have the smallest nj, this guy, and we compute how many are there, okay? And you see that for real system, the number of twins, of pairs that have this value very small is very large. To be sure of this, we reshuffle the data, and we see that this number is much lower, okay? So it means that, sorry, it means that in my experiments, there are many events that are very correlated to each other. And this is a little bit better description of how we can correlate different stuff instead of just considering if they are consecutive in time, okay? So I have to stop somewhere, because of course here is not clear if the events can be really correlated or not. So more or less I stop here, okay? Bayesi also had another idea that we tried to implement. So maybe you remember I wrote delta theta, delta t, so the area, this way. And Bayesi suggested to split the temporal and the spatial function in this way. So delta t by average t is this distance, this arc actually, and delta t is a length but also a time, because we suppose that the bubble is moving more or less at a constant velocity. Okay, so using these two, we can see that the distributions are pretty different. So in a real system, most of the data are concentrated in this area. So there is a peak of concentrations. While for the reshuffle data, randomly reshuffle, they are spread all over. And this line is more or less the point where I decided to have, is more or less this point, okay, when they start mixing each other. So if you consider a real experiment, okay, this is more or less real time, so this is much boring than my first movie. And this is the realization of the cluster that we found. More or less, we are able to understand and to detect the real cluster. You know, in experiment, you see how noisy is the image, how badly defined. But this is the best we can do, considering pixel by pixel. Okay? So, these are, imagine bubbles. These are my experiments at very low field, 0.13, 14, 15, 16. You see that increasing the field, you get larger clusters, so in some sense the cutoff is going up, and this is exactly what the size distribution gives you, okay? So there is a cutoff of small fields, and a larger field, the cutoff is large, okay? What is the exponent of this guy? Okay, I'm cheating. The lines you see there is one universality class that I'm not going to tell you immediately. But this is to say that the two good candidates to be the depending class describing the data are the quenched KPZ, the quenched Edward Wilkinson. And the size distribution exponent is 1 point something. And my data are 1 point something. So, no solution. It happens, that's life, okay? But there are two other guys who are much different. 1.2, 0.6. Oh, this is nice. This is also nice, 2.2, 3.5. So, if I can say one of the classes is the real one, maybe I should look at these two guys, which means to find the roughness exponent. So I'm coming back on time as Lamerle and try to detect the roughness exponent. So the first thing I try is to calculate the structure factor, which is a mess. Because it's a bubble, and the pixels are in a grid. And what is the reference line in a bubble? It's a circle. What's the circle? So we spend a lot of time to describe. Now I have a recipe. Yes, thanks. And once you get all the bubbles at all the times and all the fields, I construct this guy, and these are the results. For different fields, it's a perfect power law, and the exponent is of the KPZ guy, okay? Which was 2 something, the other is 3, so it's like this. This is not a fit, this is just a comparison of theories and experiment. So, I think it's KPZ, but you never know. One experiment is not enough. There is another way to detect the roughness exponent, is to consider the average size versus the length. So if you take this cluster, this is the size, I can take this as the length, and if I do the analysis, the blue points are all the data I have, but if I take the average, these are the red lines, and if I take them for all the fields I have, this is not a fit. This is just a comparison with the 0.63 prediction of the KPZ, quenched KPZ data. So is KPZ? I think so. I also have this data, but okay, it's mostly cut off, so the distribution of the length is dominated by the cutoff, so any exponents can be fitted with 2. But I think that 0.63 compared to 1 is absolutely clear, and this is confirmed by the structure factor description. So we think, Alberto thinks, and I agree with him, that this 2/3 actually is the depending exponent of the KPZ, universality class. So it's not it's not an equilibrium process. I think this is the experimental test of this. Why do you have this? Okay. Okay. Um, there are other things to try to understand. Change the sample, for instance, cobalt platinum. Try to understand what happens when you irradiate the sample with these strange figures. And also consider a creep with the DMI. So DMI changes the nature of the wall. Here, the wall is a block type with this guy, the Dalry-Skimori interaction, the block turns into nail one, and then I would like to understand why escape is easy. Okay, thank you very much. What do you think is Barkhausen noise is, I mean, classically, is when you apply a field which is changing on time. So it's the sequence on around the pinning field. So the Barkhausen noise is looking at the dynamics when you apply the field, which are the order of the pinning, or better. There are pinning points, and so this stop and go motion is the Barkhausen noise. Here you apply a fixed field, so it's just at the temperature. That's the difference. Yes, but it's exactly the average color, or if you want the average monetization. So how the monetization, because Barkhausen is dm over the t, so the change of monetization over time. So is the size of my bubble over time. So I can record it, but I can really measure. Yes, yes, Pierre. You are the theorist. Well, no, the anisotropy gives you the fact that the wall is very tiny. I mean, is narrow, and and it takes the monetization up and down. So this is a real 1D system. So the anisotropy just plays that role. It gives you the fact that it's 1D. So it's really aligned because it's 1 nanometers and it's fine. But I don't know if it's so important. Maybe there are orientation what? No, no. Ah, okay, I understand. Okay, my feeling is that you see, my cluster are slim and white. So naturally, the roughness has to be smaller than one. It's because it's a bubble. I think it's related to the fact that for some ways he has to keep the shape. Okay, but I cannot translate it immediately in something that goes directly in the KPZ term. And well, I also calculated the roughness considering the line, all the lines, and I get exactly the same value. Yes, it increases, you know, but the roughen goes saturated at a certain distance. And of course, when the bubble expands, you only are considered small distances. But I mean, the roughness there within the same distance is the same. It's true that it is growing, but I mean, it loses correlation more or less for the same distance. think it changes the cutoff. It changes the cutoff. No, the slope are these guys here. I mean, very small correlated. The cutoff is, the exponent is for small sizes. Yeah, but I know, I'm aware of this problem. Also because for different fields I have to choose different values. I'm not very happy about that, but I don't have a solution yet. No, I can tell you that the number of cluster goes a square of the radius. So I think it's very stationary. So it goes exactly as a circle expand at a constant velocity. Ah, okay, okay. We'll discuss about